Today we're talking about sound waves and sound wave sensors. In the ANSI definition, sound is an oscillation in pressure, stress, etc., propagated in a medium with internal forces or superposition of such propagation oscillations. So let's break this down a little more. What we really mean here is sound comes from vibrations. These vibrations are energy that is translated through a medium, either H2O, air, a solid, etc. How is this happening? Oscillation and pressure. So when the object vibrates, pressure differences are created through the medium by displacement of the molecules in the medium. This propagation is a waveform, which is the sound wave. Here I'm showing a physical example of a droplet in water giving off ripples. The droplet's like a vibrating source, giving off energy into the medium, causing displacements and pressure differences, which are in turn the ripples, aka the waveforms moving through the medium. There are three factors that have to do with the sound wave: frequency, velocity, and wavelength, where we can add them all together into an equation of frequency equals velocity over wavelength. Velocity referring to the wave velocity in that medium, because the velocity can change depending on what medium it is in. So next, let's do a little more deep dive. So using the equation, frequency equals velocity over the wavelength, we can show that as we change the velocity, or the medium, the frequency increases, even if it's the same wavelength. Well, side note, this is similar to light, but light has a constant speed, so it's always frequency equals the speed of light over the wavelength. So the little things to remember: in a vacuum, it's empty. There's no particles, so no sound wave propagates. There's nothing to move around or create pressure. Frequency also is measured in hertz, which the SI unit would be cycles of the wave over seconds. So in music, which is propagation of sound through air, we say pitch. Pitch is related to the specific frequency of the sound wave. These pitches are given reference terms as letters. Example, C, D, G sharp. Here I'm writing down different notes and their different frequencies. A, C, G sharp. The subscripts really are just referring to the octave. When it comes to sensing sound, the basics, we have a vibrating source, giving a propagation of pressure difference through air, hitting a diaphragm. The diaphragm then will change in either X, Y, or Z, so displacement, which will then go to some sort of apparatus, which will turn into an electrical signal. This overall transduction is a change in pressure to a change in displacement, which will then change something in the apparatus, which we'll talk about next, to electrical signal, which is a change in voltage. Now we'll talk about the four different types of sensors. The first one is called a dynamic sensor, which is based on inductance. This inductance just creates a change in the magnetic field or the electric field. What happens is a sound wave will hit the diaphragm, which is attached to a coil, which will then move over a magnetic bar. This will cause an induction of a current, so a change in voltage. The guiding relation is inductance is equal to the number of turns times the magnetic flux over the current. Next, we have piezoresistive. This is where the diaphragm moves, and it'll create stress or strain on a certain object, either a crystal, or many old microphones, it was carbon granulars, which then changes the resistance. This common formula is resistance is resistivity times the length over the area. The second two sensor types are piezoelectric, similar to the piezoresistive, but here it's a change in voltage is given off. So stress or strain on the crystal will give off an electrical discharge. Here I'm writing down the dipole moment of the crystal, which is charge over the volume. Stress and strain are related to the length change and the force on an area, which is also what's at play in the piezoresistive that I wrote earlier. Next is a condenser, which is based on capacitance. So change in capacitance happens where the diaphragm moves in and out, which is attached to one of the capacitor plates. So as the capacitor plate moves in and out, the distance between the capacitor plate changes. This can be seen governed by the equation where it's the permissivity times the area over the distance between the plates. So overall, both dynamic and piezoelectric don't require an external power source versus the other two, but both piezos deal with the stress and the strain of a crystal. Next, we're going to talk about the common types in nowadays sensors. So cell phones and pocket tuners. Both are based on the condenser or capacitance system, mostly through MEMS. This is because MEMS are cheap, already in many objects like cell phones, and they're easily miniaturizable. The problem is there's a long lag between the detection and display of what you're sensing, and it's not the most accurate source. Next is a strobe tuner, which is based on the strobe effect. This describes the phenomenon between the rate of capture and the object in motion. Example would be a moving car wheel or a strobe light. Here is a visual representation of the strobe effect. Here I'm squatting at a certain rate. With the light consistently on, you see me at every point in my squat. But if I turn the light on and off at the same frequency as my squat, it will look like I'm just standing. Now if I change the light frequency again, you will see many points in my squat because it does not match my squatting frequency. The tuner uses a similar effect to the strobe light. So we have a change in pressure, change in displacement to whatever change is used, change in voltage, which then has a change in light. So an LED will flash at the same frequency of the sound wave, and then we'll set a spinning wheel to the frequency of the note that we want. The wheel has many different levels of dots at different thicknesses and rates around. So as it spins, if it doesn't match the LED flashing, it will look blurry. If it does match, one of the levels of the black dots will match and will look like it's not moving. The disadvantage of this is that it's large and clunky, a lot of moving parts, and it needs an external power source. The advantage, though, is that it is the most accurate tuner.